Guys, in the last video, we talked about column selectivity. How selective is the column to the ions that you want to separate? Are they selective? If so, then you should get separation on your chromatogram. If it's not selective, then that means all the ions are going through and it doesn't really matter if they're separating or not, and you just get one big old fat blob that comes out at the very end of your chromatogram. Nobody wants that. So your selectivity has to be very high. Okay? Your column has to be basically doing its job, which is why you're using the chromatograph in the first place, and that separation has to occur. So that's what we just kind of got finished discussing, and we talked about how we can affect the selectivity of a column. In this video, what we're going to do is that we're going to focus on this term called efficiency. All right, so column efficiency is going to be pretty important too. Let's say, for instance, all ions of the same kind are eluted together. This is what's supposed to happen. Okay? So what that means is that chloride is in the column, and chloride is with all the other little chlorides all the way around it. They're all kind of grouped together, taking care of each other, forgetting about everybody else. And this little clump hopefully comes out of the other end all at once. Right? So ideally, this is how a chromatograph should be structured. So we know that ions go in, we know that the ions group themselves together, and we know that those ions travel through the column together and out the other end of the column into the detector all in one big clump. The issue here is that this happens typically with very small volumes. That is why that you see our loop sizes on the instruments super tiny, right? We said in the past typically 100 to 200 microliters of sample is getting injected. We have micropipetters in the laboratory. If you don't really know what 20 or 100 microliters looks like, then you need to get one of those micropipetters and you need to suck up that amount of volume and look in the tip of the micropipetter, and you're going to see a super tiny amount of liquid. And that's all the liquid that's needed to go into the column and to separate. The issue is that if we amp these large volumes up, what's going to happen is that these chlorides will have a harder time sticking together in a tight little clump. In other words, what goes on is that there's going to be tons of more chloride because you've injected tons of more sample. And this blob is going to get bigger, and the blob is going to get bigger, and that blob is going to keep getting bigger. The more and more stuff you inject into the machine, the more ion that's going to be present, and the bigger the blob is going to get. So what we would want to see on a chromatogram is a flat baseline, and let's say chloride comes off. We would want chloride to come straight up and to come straight down and go back to baseline. It's a little bit harder to do this with LC, and ion chromatography is a form of liquid chromatography. And sometimes there's nothing you can do about it. Versus gas chromatography side of the house, liquid chromatography peaks are traditionally a little bit wider. They're a little bit uglier. They have more of a slant than your traditional gas chromatograph peaks that you've always seen. All right, well, if I inject a very large amount of sample, I'm going to see a problem to occur. If I oversaturate that column and there's tons of chloride that's there, chloride will begin to come off, but chloride is going to come off in a big old chunk because there's tons of it. And I'm going to see a very wide peak. So the width of this peak is pretty important. right? We want these peaks to be narrow. That never goes away in chromatography, because if they're narrow, you've got better control of the resolution. Things can come off really close together in order of time, but those are going to be separate on the chromatogram because the resolution of the peak is super, super tight, and it's a narrow peak, and it goes straight up and it comes straight down. There's no carryover into the next time frame with another peak. Well, if we look at the width, we are going to have a term that we can use, and this term is going to be called bandwidth. So bandwidth in chromatography is basically the width of the band at the bottom. And this kind of think of as the band. We call it a peak. We could call it peak width, and people would understand what we're talking about. We say bandwidth, and people get that question wrong on an exam. Well, there's no sense in getting it wrong. It's just a different way that we refer to the same thing that we've always been talking about all this time. So what we're going to see with bandwidth is that if we have a really small value of bandwidth, then this is great. This is good, because that means that this peak is super, super narrow. So this has a very small bandwidth. Also, at the same time, these peaks are traditionally taller. And that's great. That's what we want to see. We're talking about the same amount of stuff. So if we allow this amount of stuff to come out of the column and out the other end into the detector, then this amount of stuff is going to have a particular shape. And this is what we would want to see. We want to see a narrow bandwidth and a really tall peak that gets formed. But not everything will behave that way. So if the bandwidth is high, then this is something that we refer to as a bad peak shape. So here we have a very high bandwidth. And as you can tell, this really wide bandwidth means a wide peak. And wide peaks are typically a little bit shorter. So imagine for a minute the same amount of stuff that got injected up here, right? And it gets re-injected, but there's maybe a difference in how it comes out of the column. And it doesn't come out of the column all at one time. Well, what you would see is a wider peak, but the peak has to be shorter in nature if we're talking about the same amount of material. All right? So what this is going to do, it's going to refer to what we're going to call efficiency. Efficiency of a column is how these components are coming off of the column. And these components, well, they're relying on these interactions, right? It's the whole interaction of the anion or the cation with the stationary phase. Interaction instances is actually the proper term that they use. We just don't use the word instances because it makes it a little wordy and we're just too lazy to say interaction instances. But that's kind of how it's formally referred to. Well, all of this is based on one number. Your efficiency we've talked about before. Your efficiency we talked about in the intro to chromatography in the very first lecture series. And this is basically the number of plates, right? If we're talking about the same amount of sample that's getting injected, and this is column number 1, and column number 1 gives us a narrow bandwidth with a really tall peak, then that is great. That column is suited for that anion or cation, and this is what we would want to see. Notice, though, that liquid chromatography will hardly ever look this textbook. Well, let's say that we inject the same sample onto column number 2, and in column number 2 we get a fatter peak that's a little bit shorter. The efficiency of these columns are different. That also means that the plate numbers of the columns are going to be different as well. All right, so quick review of plates. What we said before in the past is that these things are flip books, right? So plates are basically this theoretical concept that inside of the column we have these slivers. And the slivers are basically individual steps, and those slivers are what we refer to as plates. And the higher number of plates, then this gives us a better efficiency of the column. It actually flows a little bit smoother. The components will come in and they will separate a little bit better, and you get better peak shapes because of that. Again, think of a cartoon. The more individual pages with slight modifications, the smoother the cartoon will look when you begin to flip through it. As far as the number of plates, if they're really low, well, you could probably still get separation. You can still make a cartoon out of them, right? The problem is that the efficiency, though, is going to be lowered, and it's going to look a little choppy. Meaning separation is going to happen, flow is going to happen, things are going to separate, but maybe not as well. And we get these weird peak shapes that come out of the chromatogram because of that. The same would happen with a cartoon. If you're too lazy and the cartoonist doesn't draw enough pages to flip through, then things are going to be kind of jagged and a little interrupted as the cartoon flows from beginning to end. All of this plate efficiency stuff really relies on what we're going to call a particle size. So think of the stationary phase, right? And these particles we've talked about before, and these particles are loaded on the inside of that column. Okay, well, here's maybe one example, and another example of particle size, maybe a little bit bigger, and you're going to see a difference in how the anions and cations behave on the inside. To the one to the left, we have a smaller particle size. So this is a smaller particle size. And the one on the right is going to be a much larger particle size. You can see that by the way that I've drawn them. So if I inject a sample into the column and I allow the column to begin the separation, and I rely on the column to do that job, then these particles, or the sample, is going to go into the particles, and it's going to kind of take its time. And there's more individual steps here that it can kind of go through and interact with in order to improve my separation. So smaller particle size is actually going to be very good. This increases most of the time the resolution of your components, and it also increases the way that the peaks look. Okay, so that's good news. We want good resolution, and we want that textbook peak shape that we would see straight up and straight down as they come off. I don't want fat little wide peaks coming off of the chromatogram. The larger peak size over here to the right, well, this is going to behave a little differently. I inject my sample up here at the top, and the sample is just going to kind of play this game of Plinko, and there's not enough of those particles like there were on the other side, and they're going to quickly come out. So the particle size here is going to play a role. It's going to play a role in resolution. The larger the particle size, typically the resolution decreases. So your peaks become closer together. The reason is these anions or cations are not spending that much time in your column anymore. So it's taking them much less time to get out of the column, which basically floodgates the whole system, and these peaks will come off back to back to back. Your peak shape will also decrease because of that. That peak shape will tend not to be very narrow. It will also not be straight up and straight down. And things can come off in a very blobby nature, and you do not want that to happen at all. The drawback, though, small particle size means that these things are packed together a little tighter, and this is going to increase your pressure. Sometimes you might have a system that cannot handle the pressure here. There's actually a trend, though, in a laboratory now where we are putting the letter U in front of an instrument. U, HPLC, for instance. The U is going to stand for ultra high performance. And a lot of times these ultra systems are using super tiny particle sizes. And that super tiny particle size is jacking the pressure way, way, way up. And your machine has to be made in a certain way to handle all of that extra pressure that might come around. So not everyone can use super tiny particle sizes in their columns. And this is going to be a limitation of the instrument that you are using in the laboratory. The average size here for a column particle is about 5 micrometers. The 5 micron particle size. You know, HPLC world, the LC world, and again, IC is part of the LC world. It's not uncommon to see like 4.6s that are out there and 3s, but on average, we're looking at about a 5 or a 4.6, somewhere within that range. That's going to be your traditional column. Every time you look at methods that are getting done by someone else in a laboratory, it's typically always like a 4.6 to a 5 micron particle size for your column. Nothing a little bit smaller because that makes the pressure go up. And then maybe some people don't have the necessary pieces of equipment to handle that extra pressure in a lab. So that's something that is always important when you go and order a column. They will always ask you what kind of particle size do you want. And this is something that you're going to have to provide them. So your particle size is going to be very important. And the width of the column is going to be very important. And we're talking about the internal ID here, the inner diameter. And the length of your column is going to be pretty important. And typically these are given in millimeters or centimeters depending on the manufacturer. Okay? All right, so all three of these pieces really are going to determine the N, and that's the number of plates. The smaller the particle, well, your number of plates typically go up. The longer the column, your plates typically go up, right? And that N is going to be related to what we call efficiency, which is how well the column can do its job. On the inside of the column, if we're talking about qualities of columns here, kind of mentioned that, we're going to have a high quality and we're going to have a low quality column. High quality columns are basically particles that have a very uniform structure. This uniform is typically a hexagonal structure. Hexa means 6, so think of a benzene ring. That kind of matrix, three-dimensional, inside of the column is typically how you would see these particles orienting themselves all the way through top to bottom. Low quality columns, these particles that we have here, they're very loose. All right? They don't have this structured hexagonal nature to them. They're just kind of thrown in. Some areas are a little bit bigger. Some areas are a little bit smaller, meaning that it's kind of like a sponge. If you take a look at the sponge, you'll see smaller holes and you'll see bigger holes. Swiss cheese is the same way. You take a look at a piece of Swiss, well, some of the holes are much bigger and some of the holes are much smaller. Well, that's a very low quality column. So sometimes if you want to go cheap, by all means, go cheap if you do not need column efficiency through the roof, right? So if you're going to separate something, you know it's not going to have some interferences. The resolution's not really your top priority because there's only maybe 1 or 2 ions that are there, and you just need to run something, then these low quality columns are typically okay. However, most of the time in an analytical world, we have complicated samples, complicated matrices. We inject those into the instrument, And sometimes those related compounds are coming off quite close together. And if you have that type of sample, then a high quality column is going to be very important, because it's really going to drive your resolution, your calculations, your calibration curves, and it's really going to allow you to kind of pinpoint the true concentrations of things in a lab versus these low quality columns that you might see. The low quality columns, not only do they have loose particles, but the paths, because of that, can collapse. Meaning that the holes of the Swiss cheese or the holes of that sponge can actually cave in, and it can barricade a flow path up. And if this begins to happen, the efficiency of the column begins to go down. It gets distorted. It's not the same anymore as when you first put it onto the system. So these channels and these pathways, well, rock slides and avalanches are happening on them, and you can't utilize that road anymore. So you've got to find a detour. And when you find a detour, that's going to take you probably a little bit longer to get where you're going. So you're going to see a distortion of the chromatogram because of that. Because it takes a little bit longer to get where you're going, then these peaks begin to broaden a little bit on you. So you'll get the fat peaks instead of the skinny ones. Your retention times are also going to change, and that's because you've got to find these detour routes around the collapsed channels that were there. So the retention time could shift, and it could go from 1 minute, 2 minutes. It could go all the way to 3 to 4 minutes. I mean, we just don't know until we start running them. And not only that, because these avalanches and rock slides are beginning to happen, a lot of times the outlets are also going to be damaged. Things are collapsing upon itself, right? So it's a chain reaction that begins to happen. And let's say that we have a huge mountain and there's a bunch of snow and there's a little small town that sits down below. Well, this is the outlet of the column. And if these collapses begin to happen and the avalanche goes down, it's just going to wipe everything out here in the very bottom of the column. The same thing's going to happen with your stationary phases. So the outlets can be damaged because of that. They can become clogged. And if they become clogged, you'll see your pressure go up in the machine, and then the instrument shuts down. And that's because it cannot handle all of the pressure that is getting generated by your faulty, nasty, cheap column. So if you think that you're going to save yourself some money, you might in the beginning. But those columns are going to have to replace more often. The columns are going to do some damage to your samples when that begins to happen. And if you run out of sample from a client and you have to call that client up and say, I need more of this sample that was taken from 2 weeks ago, they're going to say that you're crazy because there's no way they can get a sample that was processed from 2 weeks ago. So that's one of the things that you've got to watch out for, which is why I don't feel bad if I have to spend a little bit of extra money on a good column that's going to last for quite some time. All right. So in the next video, we're going to continue to talk about these terms that are related to the column and the stationary phase on the inside. And we're going to go back and we're going to revisit void volume. So stay tuned.